All right, so we had, hello everybody, welcome back. We had a question about homework 6, a request to write out the model, so why not? So for those of you who haven't seen it yet, homework 6 is about the skills that you need to successfully play Scrabble. There is a story that goes with this homework. Would you like to hear the story, where this came from? Okay, the story requires me to drop an F-bomb, though. It's part of the story. Is that okay? You can handle that?
It's the last day of class.
It's the last day, right?
I've been waiting for one.
Yeah, well, I couldn't do it on Tuesday because my kid was here.
Oh,
So,
okay.
and he had his headphones on, but, you know, he would hear that, right? He will catch that. So it was roughly 10 years ago when I was the coordinating officer for this group of quant psych people, and they wanted to have a mid-year like board of directors meeting thing, and they had it at the place where the annual meeting was going to be, which was St. Pete's Beach, Florida. And so this was held in February, and I thought, free trip to Florida in the middle of February? Yes, I will sign up for this. So I took Jonathan with me. We weren't living together at the time, I don't think. I think this was when he was still at Georgia. And maybe, yeah, it's all blurred together. But anyway, we both went. And so it was a Saturday, and I spent the entire Saturday freezing in an overly air-conditioned hotel room being talked at by my senior colleagues. And he spent all of that Saturday on the beach, at the bar, presumably at the beach. And he came back to the hotel room at the end of the day with this cup, and it was like this big, and it was a rum runner. I don't know if you're familiar. Rum runners have like this much alcohol and there's like a little bit of something else. And he's like, "Hi, baby, how's it going?" Like, "How many of those have you had?" "I think this is 4. So he had a great day. I did not have a great day. But then we were hanging out, like waiting to decide what we were going to do about dinner. And we were playing Words with Friends. So I never played Scrabble as a child, and it turns out there is definitely a learning curve to successfully playing Scrabble or Words with Friends. And I was terrible at it initially. And so we would play, and he would just murder me. And we were playing that day, and he was literally passing out between turns. Like the phone would ding, and he'd like wake up and play a word, and then just like sink back into the pillow. Ding! Play a word, back into the pillow. And I got mad. I was like, "How are you still beating me? You're passing out between turns." He's like, "I'm fucking gifted." And, you know, he's not wrong. He's not wrong. He's not wrong. He is fucking gifted. You know, I asked him for our help. To be fair, I'm better at SAS than he is.
Of course.
So, you know, we all have our special giftedness. But it inspired me to make the homework, because before this, if you had asked me, you know, what does it take to be good at Words with Friends, I would have said you need to know a lot of words. No, you need to know where to put the words. Mm-hmm. And my spatial ability is so terrible, like I can get lost in a closet. Mm-hmm. That's why, like, I'm very bad at this, is because I don't see the places to put the, you know, the triple words and the triple letters and all that, and it took a long time before I did. Mm-hmm. So that's the moral of the story, is that it's not just about verbal ability, it's about spatial ability, particularly if you are playing fucking gifted opponents. So that's the story behind the homework. So your predictors then are a binary variable of whether you're playing an easy opponent or a hard opponent, your verbal ability, and your spatial ability. So we had a request to write out the equations that go with the models. So section 1 is asking for additive linear effects. So this is not a set of words that you've heard before, because this was the only thing you knew up until like last week. So additive is a keyword that means no interaction terms, just what we would call main effects now, where the variables are by themselves. So if I'm going to write out my equation, and I'm doing it the fast way here, Scrabble is my outcome. I've got my beta 0 intercept. I've got beta 1 times easy versus hard. And I've answered several questions about this in this case, because opponent is binary. You only need one predictor for it. You don't need separate dummy codes for easy and hard. You only need one. So this should be coded such that the easy group is 0 and the hard group is 1. And that can happen just by subtracting 1 from the original variable that was coded 1, 2 instead. So this is easier than other coding that we've had to do. Then we have beta 2 times verbal, and then I said it needed to be centered, right? Oops, hang on. Minus what? What did I say, 30? Does that sound right? Yeah. Okay. Oh, come back. There we go. And then we have beta 3 would be the next one here. And that's spatial, centered at 10. Remember? Okay. And then we'd have our E hanging out at the end. So that's your model for section 1. Additive effects, meaning there's no multiplicative combinations, and everything is a linear effect because there's no squared terms or anything that would introduce curvilinearity into the prediction. So that's section 1. Does that help? Yeah. Okay. Section 2 then starts with that. Let me get the exact words here. Estimate a model that examines the extent to which opponent type moderates the linear effect of verbal ability and opponent type moderates the linear effect of spatial ability. So we're adding 2 interaction terms for moderation. So I will come down to the next line here. So I'm going to pick up beta 4 times easy versus hard times verbal minus 30. That's one of them. Plus beta 5, easy versus hard times spatial 10. There we go. Something like that. Does that help?
Yeah, great.
So then
after
if I'm...
the beta 3 special minus 10, is there, that's a plus sign after that, yeah?
Yep. Thank you.
Okay.
Yep, I forgot it. There we go. And it decided to capitalize my beta for no reason. There we go. So then if I use this idea to try and figure out how to get simple slopes, right? What is the effect, say, of verbal ability for blah, 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 blah? So if I hear effect of verbal ability, I got to go in here, bring down everything that has verbal in it but nothing else. So I need that one. Don't need that one because it doesn't have verbal in it. Do need the interaction term, don't need that one. So those are my ingredients to get the verbal slope, and it would look the same to get the spatial slope in this case. All right, does that help answer your question? Yes? Sure, no problem. Other homework questions I can help with? No? Good with that? Okay, then as we were checking out before everyone got here, drum roll please for course evaluations. 22 out of 26. We need 2 more. So I sent out reminders yesterday to those who have not done it. It's due by Saturday night for this. And in case you're curious as to what initially drove me to try and actively recruit people to keep my response rates up, the very first semester that I taught here, I had 5 people in my class and only 2 of them filled out an evaluation. So that is not very useful data, I gotta say. So ever since then I was like, okay, I'm gonna start bribing people because I want to hear what they have to say and make sure that the results do not reflect selectivity as opposed to anything else. Because the people who fill out evaluations voluntarily either love it or hate it. And so I want everyone to participate so that they can tell me how much they love it, how much they hate it, or if they're thumb sideways about various things. So nothing will beat fall 2020, both classes, 100%.
That's insane.
Yeah, so that was good. That was a good one. That was live from my basement the entire time back then. So.
I loved that.
Live from my basement. All right, another announcement. I know what I was going to say. One thing I have not done yet, but I'm going to, is update the printable version of the syllabus to match what actually happened, as opposed to what I thought might happen at the beginning of the semester. That way you can download it and have it. That way if anyone asks, what was covered in this class, if you want to take an advanced class, you can show them the syllabus and it will be an accurate representation of what happened. And with respect to finals week, I heard back from all the TAs. 2 of them are able to have office hours, and so I have office hours across the 3 of us every single day next week. So Nikki will have it on Mondays. I'm doing it on Tuesdays and Thursdays from 12:30 to 4:30 on Zoom, and Lexi will do it on Wednesday, and then Nikki's doing it on Friday again. So if you're waiting to get caught up, it would be a great opportunity to take advantage of these extra resources. I'm going to turn in grades on Friday night or Saturday morning, and I will turn in whatever grade goes with the points that you have at that time. So if you're behind, now is a great time to get caught up. Okay, any other questions about schedule, homework, logistics? No, we're good? Okay. Then I have a brand new thing today. It's literally a brand new lecture. I finished it like 4 hours ago or something, down to the wire. What I used to do with this is sort of sprinkle it throughout the semester, and I felt like it was getting lost that way, and so now I've just decided to make it a thing. So this is about the context behind what you've learned and what types of research designs would cause you to say, yeah, I need to go take more quant methods to be able to have the models to do that. So when can you use this, when can't you? That's kind of the big picture here. But first off, summary. So the steps of the analysis, so to speak. So I started off the semester with this slide, 2 reasons why you are here. One of them may be, I just need to pass this class to meet my requirements, and I'm still okay with that, but I really hope that at the very least you gain more confidence in your abilities to be able to do this type of methodology, and that it is available to you to be able to extend the type of research that you can do. Because if you know how to do qualitative methods, then you can think to ask research questions that qualitative methods are good for. If you know how to do quantitative methods, you can think of different kinds of research questions. So hopefully you have some greater confidence and facility with these models. And as I had promised, the hard part is not the math. Now, do you believe me?
Yes.
It's language. Believe it or not, language is what makes this difficult because there's so much working memory load linking together the concepts with the notation, with the programming syntax, and making SAS, work for you and making R work for you. And then we have the decision rules, is like, what do I do first? What do I do next? What happens if this happens? What happens if that happens? That's what makes it tricky. So as much as I want you to feel good about what you've accomplished and what you're able to do now, it would be irresponsible of me to say, great, you know all of quantitative methods, good luck. Because it's really important to recognize when you don't have the tools that are necessary to address the type of research design at hand. So I want to plant the seed as to what else you might need. So first off, review then. Step 1 in a quantitative methods analysis is to understand or create the research questions to be answered and understand what kind of variables you have to answer them with. So this presupposes that your data are collected. It's a whole separate set of considerations and coursework in what kinds of research designs are most appropriate for what situations and what the trade-offs are between different choices. I'm supposing that you've already dealt with all of that. So as we said at the beginning of the semester, each variable in a research question is either going to be a predictor or an outcome. So here are the synonyms then. The textbook that I picked uses the term regressor for predictor. Independent variable they use to denote something that you care about specifically as the focal point of your analysis. It's also used, independent variable is used to describe variables that are manipulated rather than measured, like in a true experiment. And then there's the term covariate. Now, in a classical experimental design context, covariate gets thrown in whenever you have a quantitative measure that is just something you control for and you don't really care about. But to me, mathematically, regressors, independent variables, and covariates are all the same. It's how you think about what they mean to you that changes how you would talk about them and the conclusions that you would draw. The math don't care. These are all X's as far as SAS or state is concerned. And then outcome has fewer synonyms, but dependent variable certainly is one, and criterion in the context of regression models specifically. And then the big question, what kind of variable is it? Where the major categories to be distinguished is quantitative versus categorical. So quantitative is where the numbers are numbers. Categorical is that you may have numbers, but they're really just labels for different kinds of groups or situations or what have you. And I will note that the models that we did this semester are for quantitative outcomes only. There are other models for other kinds of outcomes. So step 3, note that I skipped one on purpose. Determine how to include the predictor variables in the models. So if you have a quantitative variable, I would strongly encourage you to center it. Centering means subtracting a constant so that 0 is meaningful. Why do we do this? To make the intercept meaningful at a minimum in all models. But then as we've seen in the context of interaction terms, if we don't center the predictors, their effects are going to be at the 0 value of the moderator. And so if 0 is not a meaningful point, that slope doesn't help you. So it can actually cause estimation problems in advanced models if 0 is too far away from the data. So I start with that, like 0 needs to mean something. The good news is that if you forget this step, or if you pick a constant that is not terribly in the middle, your predicted outcomes, your model R-square, all of it's going to be the same. So there's no wrong choices for centering, only things that are weird or less useful. Beyond just that, though, we want to think about what kind of relationship a quantitative predictor could potentially have with an outcome. So linear is the default. And a lot of your textbook sticks with just linear at the beginning, and then they have like extra chapters towards the end for other possibilities. But I chose to do it the other way because I want you thinking about this from the get-go. So linear assumes that the slope keeps going, that a 1-unit change in x has the same impact at y regardless of where you are on x, and that's probably not possible. So quadratic is an alternative. That's an easy one to add to the model because you just square your predictor. That is designed for slopes that might change directions, so it might go up and then come back down, or go down and come back up. Exponential is a type of slope that kind of shuts off, so it looks like it starts to asymptote at a point. You can cheat your way into an exponential slope if you log transform a predictor and then fit a linear slope to that. That creates an exponential curve. We also saw piecewise models, or what some might call linear splines. That's where we cut a variable up into sections and fit a slope that's for different sections. That's useful for predictors that have demarcation as to what certain values mean. Like if you're above 15, this means something, and if you're below 15, that means something else. Those types of variables might work well for piecewise effects. But the bottom line is that the data can always help you to decide. So you can always add a term to the model, see if it helps. Then you know that you need it. So you don't have to guess. But it's good to think about these things from a theoretical standpoint first, like what is a reasonable shape of relationship, and then how do I specify that in a model, given what's reasonable to expect. So, questions so far? Good? Okay. Then categorical predictors. So the big thing, if you remember nothing else this semester, do not put a categorical predictor into the model directly. Because if it isn't really a number, getting a single slope for the change in y per unit change and not a number is not going to help you. It's not going to mean anything. So the way that we've approached this is by taking categorical predictors and turning them into a series of binary variables where it's either 0 or 1. And there are 2 different coding schemes that I demonstrated amongst infinitely many, but these are the 2 that I think are most useful. And I have them compared here, where the difference between them is in the blue shaded part. So indicator coding, which works optimally for nominal variables, is which you designate one category as the model reference. So that will be the fixed intercept will give its predicted outcome directly. So in this case, I've designated group A. And because I have 4 possible groups, I need 3 new binary variables. And I've named them for what they mean, given this coding scheme. So A versus B is called that because the value for group B takes a 1 when it's group B and 0 otherwise. Likewise, the second one is going to give me A versus C, and the last one is going to give me A versus D. So in this coding scheme, there's only 1 once in each of these. So it's like it's that one, that group's difference. In contrast, sequential coding, there's multiple ones, because this works as a series of thresholds, essentially. So the names of these variables have changed because what the coding scheme creates has changed. This one is still going to be A versus B, but by filling up the remaining categories with 1s instead of 0s, it switches the interpretation of the remaining slopes. So this is going to be B versus C because that's the point at which it switches from 0 to 1. And this one is going to give me C versus D because that's the point at which it switches from 0 to 1. There is a whole nother set of coding schemes that's known as effect coding, where you use plus or minus ones. I personally don't like those because then 0 does not pertain to any specific group. It pertains to an average across groups, which is not a representative category. So I don't like that kind, but you will see that as well. And by the way, what if I told you that all of your software will do this coding for you if you know how to ask? Like all the code that you wrote, you didn't actually have to do that. Now, I deliberately hid this from you because I want you to know what it's doing. Like, it does it for me. What's it mean? I don't know, it just did it for me. Like, that's what I don't want. And if you know how to set this up yourself, then you can make choices at the beginning as to how you want to represent your group differences, and you can get exactly what you want back. When you let the program do it, there's less flexibility. But the way that you would do that is by making what's known as a factor variable. And there, in the last unit that I didn't have time for, that I posted materials from a previous class, I have demonstrated how to do that. So that is something I deliberately decided not to show you. My bad. So we got that much. All right. Any questions on coding about this? Okay, moving right along then. Step 4, get what else you need that isn't given directly. So what you're going to get by default when you fit a model is the f-test and results for the model R-square. You're going to get the estimate, standard error, test statistic, and p-value for each intercept or slope you request. So then the question is, what research questions do you still have that aren't answered by the things you get by default? So for example, you might want to figure out what the predicted outcome is for a non-reference group so that you can report the predicted mean for group A and the predicted mean for group B and all of those things. That's a linear combination. Likewise, you might need to compute a new slope out of existing slopes, such as if you want the other predictor category differences. So in the previous slide here, in neither coding scheme am I going to get the difference between group B and group D. That will not be given, but it's in there. Because if the model knows how to make the mean for B and the model knows how to make the mean for D, it knows how to make the mean difference. It's just a linear combination of, in this case, it would be A versus B is the -1 and A versus D is the 1 to get the difference between the two. So you can subtract these two slopes to get the remaining contrasts. That's one example. You might also want to look at differences between fixed slopes. So for instance, if you fit piecewise slopes, a test of whether or not you need separate slopes is, are these slopes the same? If the slopes are equal to each other, you only need 1, not 2. Also, for predictor slopes that are on the same scale. So for instance, if you only have an hour, is it better for your health to spend that hour exercising, or is it better for your health to spend that hour taking a nap? Like, that's the kind of question you can ask, like, because it's both like a unit of an hour. So if you have predictors that are on a similar scale and you're interested as to which one matters more, comparing the predictor slopes would answer that question. And then last but not least, as you now know how to do, we can fit conditional slopes for predictors at other values of the moderator besides 0. So for instance, in your homework, what is the effect of verbability if you're playing an easy opponent? That's going to be given directly by the model because easy is the reference group. What's given not directly is what is the effect of verbal ability for the difficult opponent group, but that's a linear combination. And you can get that with those two. Another thing you might need to ask for is lumping slopes together. So if a predictor takes more than one slope to fully describe its relationship with an outcome, such as for categorical predictors or such as for piecewise slopes, you can lump the slopes back together to get an overall f-test of how much that slope contributes to the model. Same thing with model R-square. An f-test will tell you whether a new set of slopes significantly improves the amount of explained variance and avoids having to do it in a stepwise fashion where the order is ambiguous. So these are all instances of us using the model results to create new terms that would be useful to us in answering research questions. Effect sizes, step 5. Why do we need effect sizes? Because significance is not the end of the story. If you have a significant slope, it could be because it's a strong effect, you got a big sample, or some combination thereof. So we always want to convey effect size that is independent of sample size as part of our story. And I would say always okay to do is to take your t-test statistic and convert it into a partial R or a partial D. And you've practiced that in your homework, and there's lots of code examples for that. That provides the size of the effect for it relative to it plus the residual. So like, of the amount of variance that's unexplained, how much did this predictor get? That is potentially confusing if you try to think about it in terms of how it relates to model R squared, because it doesn't. That's not what it's for. It can be artificially inflated by adding predictors that explain the residual variance. So this is the idea of like a pie. Like if I eat half the pie and I leave the other half for you, this effect size would say, out of the half that I didn't eat, how much did you get? But out of the half I didn't eat is ambiguous because you don't necessarily know how much I had. So out of what's left it's a moving target. What can be okay instead, per slope, is to do semi-partial eta squared, which is directly the amount of the model R square that predictor got. It's okay for some cases, but not always. So if you have categorical predictor slopes, you need to lump them together because you can't just add up their semi-partial eta squares because of their redundancy. Likewise, for predictors that are involved in interaction terms, you have to remember that their effect sizes are going to be conditional in the same way that their interpretation is conditional. So it gets a little tricky with what to report. But I like the idea of semi-partial R square if possible per predictor. Then if you want per slope, you can do something with this as well. But at least giving them enough information to judge effect size of any kind would be an improvement over what typically happens. Okay, any questions on effect size while we're on this page? Okay, the last part, write it up and turn it in. You all know the two different kinds of dissertations there are, right? There's only two. Done and not done. That's it. There's no other demarcation that matters.
Yep.
You need the done kind. So writing it up then and turning it in, hopefully across this semester you've seen my examples of what results sections would look like for different pieces of what we've done, and your homework is designed to help you learn how to write them, because results sections are highly formulaic. That's why the computer can figure out what it should say based on the homework generator. The reality is that a successful results section is not going to describe every single thing you ever looked at. You're going to have to cut it down to just the parts that advance your story, hopefully doing so honestly. And the things that you would include then, you should have a paragraph that has a subheading called something like analytic method. Sometimes that goes at the end of your method section, and sometimes that goes at the beginning of the results. But you would describe your general approach. So for instance, I used general linear models. I used R software version whatever. I centered my predictors this way. I set up my categorical predictors so that this group was the reference. All of that sort of background information that your reader needs to have to be able to potentially duplicate your analyses in the future. Equations can be helpful if they're done correctly. So you'll want to use the proper notation if you go with this step, meaning use the equation editor to make the betas and everything properly. Then what happened? So it's important to provide all of the statistical results, the F's, the T's, the P's, all that stuff, but then also try to explain to your reader why you're telling them this. So what does it mean that your model is significant? Like that's not a conclusion, that's not a result. My model is significant, comma, indicating that my outcome was successfully predicted by these predictors with this level of R square. So every sentence, my general format is stat, comma, such that, indicating that, like that sort of, then the translation, because your reader needs the part that they can highlight with their yellow highlighter, and they're not going to highlight the F, I can guarantee it. So what you should report then, either in the text or in a table, per slope, estimate, standard error, p-value, and hopefully some kind of effect size per model would be F, all the degrees of freedom, the amount of residual variance, the p-value, and the r-square, and then keeping the reader with you. So not just, this is my model, but in response to research question 1 about blah, I fit this model, here's what happened. Thus, my hypothesis was supported, blah, 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 or my hypothesis was not supported. Like, all of that has to be woven through to keep them with you. And one thing additional that you probably haven't seen very much yet, but I think is underrated in its importance, is the supplemental material. So you can put online appendices for every journal that has extra results that you didn't have time for, in terms of the paper itself, a more complete reporting. If you had to do something relatively complicated or unfamiliar to your audience, you might throw equations and syntax in there. And this type of extra material, where you're leaving a trail of breadcrumbs for the other people in your field to follow, can get you cited. So you will say, like, I followed the approach given in Hoffman 2007 because I put a SAS program online that did my analyses, and they took the SAS program, and so now I get cited just because of my supplemental material. So I would encourage that. It also helps convey to anybody who's confused about what you did, if they can see your code, okay, I know what you did now. So, and then it's a more clear representation. So this is my recommendation as to what should all be included when you write it up and turn it in. So questions on any of that? All right. So then what did we cover this semester? The big umbrella term for the models that you learned is general linear models. The idea is that we're predicting one conditionally normal outcome per person, and I'll define those terms in just a moment. But more specifically, when you describe to other people in a results section what you did, I would phrase it this way. Like, you could say, I had a single quantitative predictor, in parentheses, i.e. simple linear regression. Because there will be people who know it only with these words, and there will be people who only know it this way. So these are the terms that go with the different types of models. So if you have categorical predictors, people would call that analysis of variance. The simplest case where you have only a two-group predictor would be considered an independent samples t-test. So these are just all specific flavors of what is really just one underlying model. And we did moderation to some extent. Like I said, Unit 7 is posted online, the one that we didn't get a chance to get to. So this is what we did. So now the bad news. In order for the results of these analyses to be believable, then we need to have faith that the assumptions that we're making are reasonable. And if we are wrong, so the phrase for this you will see is if you have assumption violations, kind of like a moving violation, like if you get a speeding ticket, like this is an assumption violation. There are two different types of consequences. One is that you can get the wrong fixed effect estimates, so the number that the slope is or the intercept is. And if that happens, then the story that you're trying to tell with respect to how the variables relate to each other is potentially incorrect. This type of assumption violation is labeled as primary in your textbook. The second kind is with respect to the fixed effect standard errors. So any assumption violation that has to do with variance is going to translate into problems with your standard errors. So if you get the wrong estimate of inconsistency, so for instance, if your standard error is too small, so let's do the math. If I have estimate over standard error, that gives me t, and my p-value goes with t. Well, if my standard error is too small, t is going to be too big, p is going to be too small. So you can end up with significant results that aren't really significant because the standard error by which you're indexing expected inconsistency is too small. It can go the other way too. You can have standard errors that are too big, and then you are shooting yourself in the foot with respect to that. So it can go either way. There is a lot of confusion out there as to what actually is an assumption and what's not. So let's go over this. First one, is linearity an assumption? No. You will see this in textbooks, you will see this in articles, but no, it is not. The reason people say that linearity is an assumption is because most of the time, if you have a quantitative predictor, they only fit a linear slope. Then that's the assumption. The assumption that you're making is that your model is correct. So if you say your slope is linear, you better be right. If you say your slope is quadratic, you better be right. If you say that you need 3 slopes for 4 groups, you better be right. So the assumption is that the functional form of the model is correct, not that it's linear. It's only linear if that's what you put in, if that's what you ordered, so to speak. So we can have nonlinear relationships represented in this framework. The term nonlinear, though, has 2 different definitions that I want you to be aware of. There is nonlinear in the variables, and that's what we have done by adding, say, quadratic terms, because that allows the relationship between a predictor and an outcome to have a curvilinear shape, but it's still in a linear model. The other alternative is nonlinear in the parameters, which describes any type of model that doesn't follow this constant times variable plus constant times variable form. So for instance, this is what's known as an exponential model, a truly exponential model. It has beta 0 is going to be some kind of intercept or asymptote. Then we have beta 1 as a slope, multiplying this term, which is e, raised to the power of another slope times x. That's nonlinear. So that's a whole different ballgame. Those are much harder to estimate and much, much less common. So we can indeed have nonlinear relationships as long as they're specified in this slope times variable plus slope times variable plus slope times variable kind of way. So we are assuming that our model is correct. So if you need curvilinear relationships, they should be in there. Otherwise, your description of how that variable relates to the outcome is not going to be complete. Likewise, interaction terms. If you assume that these effects are additive, but they should be multiplicative, then your answers are not going to be right. So it's an easier way to think about what you're assuming with respect to what goes in the model is assuming that you're correct. That anything that's not in the model doesn't belong there, and that you've got everything that matters. Now, can you ever know that in practice? No, because you don't know what you're missing. There may be another variable out there that you should have included, but if you didn't measure it in your study, what are you going to do? There's nothing you can do. So we do the best we can with the job, the materials that we have. Okay, so questions on that? No? No? Okay. How about normality? This is a tricky one. Normality of what? Of the predictors? No. Your predictor variables have no assumptions put on them whatsoever. They can be any kind of distribution, any kind of type. Otherwise, we couldn't have ANOVA as a thing. If predictors had to be normally distributed, there's no way that we could look at group differences. So that can't be it. Of the original marginal outcome, also no. It is not true that outcomes have to be normal. Here's the clarification. What we're assuming with our general linear model specifically is that the E residuals follow a normal distribution. So the terminology for this is the conditional distribution or the conditional outcome, meaning the part of Y that's left over after the predictors have had their say. The leftover Y has to be normal. And we describe, and that's because the way that we're fitting this model is predicting the conditional mean for each person, so the y hat, and we're estimating one number as the residual variance, right? Mean square error is one thing. So we're assuming that the residuals can be characterized by just knowing these 2 variables. Basically, what is the predicted mean for each person, and what is the residual variance that they all share. So this is why some well-meaning textbooks they have chapters about outlier analysis and data cleaning before there's even a model involved. Disregard those. Because there's no way to say that your assumptions are violated unless it's in the context of a model, because that's when residuals come into play. So you can't just look at the distributions of the variables and say, oh, this isn't going to work. You won't know that until you have a model to work with. And then you've got to look at the E's specifically. So the one that is trickier is what goes along with the normal distribution is this idea that I've said more succinctly as constant variance. It's the idea that the variability of the E's is shared by everyone in the sample, that there's not subsets of people for whom the model works better or worse with respect to being able to characterize their outcome. The technical term for this assumption is homoscedasticity. How's that for a GRE word? Or homogeneity of variance. So that's depicted in this picture right here. What they're trying to show is that around this blue regression line, we would expect that the residuals have a mean of 0 because the regression line is in the middle, and then we have the same amount of variability around the line at every point on the line. Otherwise, you have a term that is heteroscedasticity, or heterogeneity of variance, or what I would call not constant. And that means that the model predicts differentially well as a function of either the predictor or the predicted outcome. So I borrowed this picture because I thought this was the clearest way to describe it. Good, not good. Good, the idea that the residuals are evenly distributed. Not good, the residuals have more spread around the line, more variability the higher up you go. So this would indicate that the model does a less good job here than it does here. Now, where the problem comes in is if your data look like this, and you estimate one residual variance that everybody's supposed to share, that number is going to be too big for these people, it'll be okay for the middle people, and it'll be too small for these people. So one size does not fit all, in contrary to what the t-shirts say. Hats don't also fit all, by the way.
Maybe not.
You have to have kind of a small head to wear a hat off the shelf, I have learned. I have learned this because my father has a ginormous head. And yes, you cannot, but you can if you go online. Bigheadcaps.com. I swear to God, it's a place. You can buy giant hats. Bigheadcaps.com. And there's probably millions of others, but anywho. So this one is the sneakier one, because you have to go looking for it to know that it's there. So when might this happen is when you're predicting quantitative outcomes that have natural boundaries because of the way that they're measured. So for instance, if I have proportion correct, the lowest I can get is 0 and the best I can do is 1. If I get 100%, so the variability around those points is going to be minimal towards the ends, and it's going to get bigger as you move towards the middle because they can't go past the ends. Same thing with a count outcome. So the number of things that have happened doesn't go below 0. So the residual variance is usually going to increase with the predicted count. So here's an example of what that might look like from my other class, generalized linear models. This is an outcome which is the result of an experiment designed to piss people off. That was its purpose. It worked. And this is a distribution of the number of mean things said in response to this manipulation. Most people in the sample held their tongue. 45% said 0 mean things. This person said 24. True data. So we have the original marginal distribution is definitely not normal, but it doesn't have to be. What we want to look at is the residuals after the model has been fitted. And so after we put in all the predictors for why some people would say more mean things than others, here's what the residuals look like. That ain't normal. More problematically, though, is the spread of the residuals around the line here. The variability increases the further out you go. So there's less variance here than here. So this is an example of heteroscedasticity, non-constant variance. And this thing is called a QQ plot. It shows if the data are actually the distribution they're supposed to be, all the points should be on the line, and they're not. So we need a new different model for something like this. So non-normality is not so big of a deal. It's the non-constant variance that screws things up. Because if some parts of the model have too much error assumed and some have not enough, then everything can be off with respect to the p-values. So the way that we can fix this within the same modeling framework is to change the way the standard errors are computed. So there is something out there which is known as heterogeneity consistent standard errors. And there is a sentence in your textbook that I love where they totally punted on explaining this. And they said, these defy non-mathematical explanation. Fair. If the textbook author can't figure it out, then what hope do I have? I've heard of them, to be honest. I don't understand all of the distinctions between them. but it is a way to try to use the residuals to figure out how much variance there should be under an assumption that the variance doesn't all have to be the same. And it is an option that you can easily specify in your software. The other choices that you have are to do resampling type techniques to get standard errors, such as jackknifing or more commonly bootstrapping. Have you heard of this term before in anything? A little bit, maybe? Bootstrapping.
In life.
In life?
Yeah.
Yeah, like bootstrapping is like pulling yourself up by the bootstraps or
Yes.
something. It's
Yeah.
some kind of metaphor for it. What it means in this context is using the data that you have to pretend like you have access to all the repeated samples from the population. So you resample with replacement repeatedly from just your data, fit the model, figure out what the estimates would be, and then plot all the estimates. And then the variability of the estimates in those resampled bootstrap samples is your empirical standard error. So this is actually not that hard to do. Here's an example from the Chapter 2 data where we were predicting cognition. So this is what we just finished. The distribution of the residuals looks pretty normal. It's not that far off, but we have heterogeneity of variance as a function of the predictor. And I happen to know why this is, because I made these data up. And this model is missing 2 interaction terms that I eventually get to in Chapter 2. So read it in papers but didn't know what it meant? Good. Yeah, it's resampling is what it is. So this is the potential issue that we might be concerned about. So here's how we might fix it. In SAS, ProcGLM doesn't have anything for this, but we can switch to ProcReg, which stands for regression. And there's options that we can add to get these empirical standard errors. So here's what happened originally in this column, and then we have the new version out here. And what we can see just from eyeballing it is that these are pretty much the same, except for the ones involving dementia group, because that's where the interaction term is missing. So it changes the ones that need to be changed, but otherwise leaves them alone. And this is about the best case scenario because I made up the data to be normally distributed with constant variance for the residuals. In contrast, what about the income data that we played with in the earlier part of the semester? Well, normality is, but this is the problem. So the residual variance increases as predicted income increases. Basically down here, there's only a few different ways that you can be wrong if you predict someone makes no money. The more money that you predict they make, the more wrong you can be. Stands to reason. So income is a bounded continuous variable. It's not really continuous like it's supposed to be. So I fed that back into Stata, adding this little option right here, VCE, controls what type of standard errors you get. And the original results are right here on the left. The robust results, as they are labeled here, are on the right. And these are quite different in some cases. So the L versus U contrast in particular, the standard error doubled. And it's no longer significant. So that tells me right there that the group that is concerned with the upper probably has different variance than the group that's a lower. And it grew the standard error to try and appropriately acknowledge that difference in variance. On the bottom is what we get if we did bootstrapping instead. And the numbers don't match. So which one you pick does indeed matter. But it's the same issue, though, in terms of these are all very different than what you would have under an assumption of homogeneity. So this is something to watch out for, potentially. If you have plots where you can see the residuals are not evenly distributed, you might want to look at the results with these corrections and to see to what extent it matters that you apply them. R has an example. I ran out of time, so I linked to someone else's example. But it involves 2 different packages. So you have to do a little bit extra stuff with that. All right, how we doing? Okay, so this is caveat to what you've learned. Watch for this as a problem, and then know you have options to fix it while staying within the modeling framework that we've been working in. Another issue that you may have to deal with is outliers. And not the good kind, not the Malcolm Gladwell outlier kind, but the, you're messing up my model kind. And the terminology for this is potentially confusing as well. There's 3 different terms that people use somewhat interchangeably. The definitions that I've seen, though, I've got here, and this is what your textbook says, Distance is a term for an observation that is extreme with respect to the outcome. So B up here is far away from everybody else. Leverage is a term that means that they are relatively extreme on the predictors. So A is out here. So neither of these cases, though, is going to hurt the model with respect to being weird. C is another story, though. So C has what's known as influence, meaning that it's extreme in both directions at the same time. And in fact, this flat slope that's the dotted line is what you would get if C wasn't here. And if you add C, the line becomes more positive because it's trying to fit a line that includes this point too. So the problem to worry about potentially is whether this one person should have more say on what the regression line is than any other person. And there are statistics that you can ask for in your data set that will compute basically how much the results would change if you threw each person out, and it will do it for every single person in an iterative fashion, so you don't have to do it yourself, it will do it. And you might consider looking at those statistics if you're concerned about outlying observations. But what to do with them is the tricky part. Now, the textbook punts on this, and they say, well, check for data entry errors. And they're just assuming that no one could be this weird unless this was a data entry error. But no, it could be a real value. So like if I'm asking how many text messages do you send a day, and I give this survey about this to my stepdaughter, and she says, I send approximately 8 million text messages a day, that is going to be aberrant perhaps relative to the rest of my sample, but it's true. So do I kick her out? Like if it's real data? And then what about like the next person? What about someone who sends 6 million text messages a day instead of 8 million? And where do you stop? It's kind of like trying to trim your own bangs. Has anyone made that mistake? You start to trim your bangs and then like this is uneven, so you cut it a little higher and now it's uneven this way, and you keep going and eventually you have like no hair left, right? Outlier analysis can be like that. So where you might stop cutting and where someone else might stop cutting are different points. And why are you throwing away data? So I would not recommend that. Are there ethical considerations around moving outliers? I think there are. So if you're removing an outlier because the data they gave you are garbage, like if you, as an example from this class, when I look at your quizzes, it tells me how long you spent on the quiz. And for some of you, it says things like 3,612 minutes on this quiz.
Yes.
No, I did not think that you sat there for 3,000 minutes. What I think happened is you left the window open, went to the rest of your life, and maybe came back 3 days later and finished the quiz. Like, that's what I think happened. But if I wanted to use 3,000 minutes as your response time to indicate your facility with the material, like, that's garbage data. So throwing out somebody because they gave you garbage data that it can't be true, that's an easy one. But if it's real data, then and you throw them out, that's arbitrary, number one, but then you're limiting who you can draw conclusions about as well. So I don't think you throw data out. I think you get a new model. That's what I think. What new model, you ask? I'm glad you asked. When to eject. So that's the rest of this here is what don't you know yet that you could potentially need to know? So for some types of outcomes, this idea of a normal residual with constant variance is just not going to happen. It's not possible. And that's where we need to eject to a different type of model. So this semester we did general linear models. The next class that I would recommend that you take, it's offered every spring, is generalized linear models, where that ized part means some kind of not normal. So these models take what you've learned and they add 2 more features. They swap out the assumption of normal for some other type of distribution that's a better match for the kind of data it is, and it adds something called a link function, which is a transformation that allows the predicted outcomes to stay within the boundaries so that you don't get things like predicted minus 12 counts or something like that. So that class is what I would do as a follow-up, and I made it as a follow-up to this class deliberately. So this may not be something you've seen in your program of study because it's a new number that just got added over the past year, but that class covers generalized models as well as multivariate models, And it also covers something called quantile regression, which is what you would do in this situation about these people here. So do you remember like the first week of class when we talked about measures of central tendency? Mean, mode, what was the other M word? Median, yeah,
Median.
yeah. So the median is the middleist value. So it is unbiased by people who spent 3,000 minutes on their quiz, right? They're still in the middle. It is a robust estimate of central tendency, as people say. So rather than trying to predict the conditional mean for each person, what quantile regression does is predict the conditional median. And that way the influence of outliers doesn't matter as much. And if you can predict the median, you can predict any percentile. So that's a technique that I didn't learn until too late. I think is super useful for that. So if you have concerns about outliers, that's what I would point you toward instead, is quantile regression. It is exactly the same as what we did. There's no new skills involved other than specifying that type of model in the software. So it's an easy reach. The big one, and here's the thing. I know we're approaching 3 o'clock and it's the last day of class. You cannot use these models if you have dependent data. Now, what do I mean by that? The primary biggest assumption that you can break your model with and your results will be garbage if you don't know this is the residuals have to be independent for these models. That means that all the reasons why the residuals from, say, 2 people might be more related are in the model already, so then they're independent. So if I think that people from the same group are going to be more related, I put in group. And after I control for group, they should be unrelated. So this assumption is part of a terminology that you may see in stats textbooks that's IID. That stands for independently and identically distributed. So we're talking about the first part here. Now, when would this not be true? For instance, if I have a pre-test, post-test design, I want to predict test score, but I've got 2 scores for each person. Even after I control for every other predictor I care about, the fact that those 2 data points came from the same person is going to mean they're related, always. And that has to become part of your model, otherwise all of the conclusions are suspect. In a more complex case, you can expect dependency or non-independence anytime you are sampling over multiple dimensions at the same time. So if you want to do a study about elementary school students, and the only way that you can get a large enough sample size is to go to different schools to get all the kids, you have dependency. Because kids from the same school are probably going to be more alike than kids from different schools. That means that relationship that is induced by common school has to be in your model somehow. And GLMs are not designed for that. Likewise, if I have longitudinal data, if I ask people the same question every day for a week, their responses are going to be related because of who they are, even after controlling for the predictors. So this is the big one. If you have a sampling design where there's more than one type of sampling happening at the same time, you cannot use general linear models. You cannot. They will lead to way wrong answers, both with respect to the estimates, the standard errors, the p-values, everything. So part of the issue is that correlation introduces redundancy. So think of it this way. You're trying to sample elementary school kids. You go to multiple schools. If all the kids who go to the same school are exactly alike, and you thought you had 30 kids, you kind of only have 1 if they're exactly alike in terms of the unique information they provide. So somewhere between the number of kids, if they're truly independent, and the number of schools is your actual effective sample size for how much information you have. So all the standard errors where there's n in them, all that's going to be wrong. It has to be adjusted for that. But the bigger issue is that when you have this sort of layered sampling design like students in schools, every student predictor is also a school predictor. Because the context that an individual is in matters. So in that case, like if I had something like free lunch status as a predictor of students' academic achievement, well, for an individual child that might matter. But do you think there's also an impact of going to a school where lots of the children qualify for free lunch. Like, what is that a proxy for? Do you think that school might have fewer resources? Probably. And do you think fewer resources is a bad thing? Probably. So even though you're thinking about this as a child characteristic, to the extent that the kids are similar, it's also a school thing. And the effect of school poverty on school level performance is different than the effect of individual poverty on individual performance, because those are two different things on two different scales and two different constructs. Likewise, if I had longitudinal data, so if I ask you every day for a week how stressed you are and how healthy you feel, some people are going to say that they're stressed all the time and they feel like crap all the time. So the extent to which people who are more stressed on average feel worse than other people is one way that stress and health could be related. But on a given day, if I'm more stressed out than I usually am, do I feel worse than I usually do? That's a different way that stress and health can be related to each other. It's two different things. So for those reasons, if you are in a sampling design where you have multiple types of sampling simultaneously, we can't use general linear models. Yeah.
Could we correct for that? Like, I'm going to go with the pre and post one because I feel like that's the one that makes sense in my small brain. Could I separate them and then do a general model over here and a general model over here?
You could, but then you wouldn't be able to predict their change.
Okay, I understand.
So the most correct way to do this would be to fit what's known as a multivariate model, or repeated measures, where I predict pre-test and I predict post-test simultaneously, and I tell the model to put in a correlation between those two variables. Then the dependency is part of the model. It understands that these are coming from the same person and that there's less unique information than you might think if I had two different sets of people.
And that type of thing, for that specific example, is like class 3 after generalized?
Nope, it's covered in generalized.
Okay.
So we start with these sorts of, like the easier version of dependency where it's real cut and dry like that.
Yeah.
In generalized, and we do
Okay.
multivariate models. These ones, though, thank you for asking. What a nice segue into the next slide. The next ones after that, if you know that you're going to be working with students who are sampled from multiple teachers, from multiple schools, from multiple school districts, like that kind of layered stuff, you need a multi-level model to do that properly.
Okay.
So multi-level models. The key idea, this is my primary area of research, so these are like my babies, right? That's my thing. Everything is a multi-level model. The key idea is that what they do is estimate a separate type of E residual variance for each kind of sampling. So you would have an E that describes why some kids are different from other kids. You'd have another type of E that describes why some teachers are different from other teachers. Another type of E that describes why some schools are different than other schools. And then you would have school predictors that explain the school variance, teacher predictors that explain the teacher variance, kid predictors that explain the kid variance. So it's like a regression lasagna, like it's all the layers kind of weave together at the same time. And so that would be the next sets of classes. So this idea of multi-level also goes by the name mixed effects models, and it also goes by the term HLM, or hierarchical linear models. So you'll see these terms used in papers. It gets introduced in design of experiments, which is going to be offered this fall, and you all will be ready to take that. This would be a good follow-up course before generalized in the spring. And then there's 2 new courses that I put on the books last year that you may not have heard of that cover different applications of multi-level. So I've linked to all the classes here, as well as to a tutorial that I just published in Annual Review of Psychology on uses of multi-level models. So all of these things differ in how the models get estimated, which is why to do it properly, I didn't want to cover it in this class because I'd have to switch to a completely different way of talking about things. And the least squares way doesn't work very well. It's where people sort of started out but have moved on. So I put all of the idea of repeated measure stuff into these additional courses instead. So there are some ways of correcting it without doing the full model, but they all have problems. So if you have this type of layered sampling, this is what you're really going to need. And every single thing you've learned applies. So it's just a question of adding more stuff to your toolbox, not that you've wasted your time. I promise.
It's an important note.
No, it's very important
It
because
is.
honestly, I have people who come to multi-level who don't have a solid foundation of linear models and slopes and all that stuff, and it's way harder for them because they don't understand just the basics of how to put predictors in and how to ask for things.
Mhm.
So everything you've earned, you've earned. You've earned and you've learned, damn it. It will come back. It will be useful to you. It's just we're going to add stuff to it is the thing. All right. Last but not least, one more pitch, measurement error. So the idea that what we've measured is probably not perfect. We would want to worry about reliability of our measurement. So for items in a scale, we might have that. For coding things, we might worry about inter-rater reliability. All of these models that use observed variables only assume that there's no measurement error at play. That's probably not true in social sciences like ours, where we're constantly looking at squishy constructs. So by squishy, I mean the opposite of things like height, weight, Kelvin, moles, gigawatts, like all the terms that are like you can measure them perfectly. That's a Back to the Future reference, a gigawatt. I'm told it's not a thing, but it seems like it could be.
Yeah, sounds like it.
Well, I mean, that's how the flux capacitor works, clearly. So, but we measure things like aptitude, or what's another one to think of, like conservatism, or grit, like things that are squishier, right? We give out surveys with multiple items, and we add up the items on the survey, and we hope that that measures something, and we might have to calculate a reliability coefficient like Cronbach's alpha, which is useless, by the way, and then we just leave it alone. We don't do anything about it in analyses. But what if we could? Well, we'd probably get better results, because if you don't measure something well and you try to put it in the model to control for it, you're not really controlling for it as well as you could. So all of the relationships are going to be messed with in some capacity by measurement error, both good and bad. So this is where the world of the other half sort of our curriculum, the idea of measurement or psychometric models comes in, latent variables. Rather than trying to add up all the items together and say that this is my scale score, what if we tried to represent their commonality with the latent variable? We could do so and separate out the variability that's in common, that's supposed to be whatever the thing is that you're measuring, from the variability that's unique to each item, which is considered error. So the role of latent variables, which are unobserved, but they're indexed by covariance, by relationships between variables, is to create an outcome that's more reliable, that can then be a predictor or an outcome as you need to. So other courses, such as item response theory, or IRT as it's known, factor analysis, and structural equation models, are designed to do general linear model type things on latent variables instead, so that they can be measured as well as possible. And I'm doing that in the fall, but I would not recommend that one as the next step. That's a huge jump between then and that. So if you're interested, if this has piqued your curiosity about what else is out there, and you're not sure which ones would be most useful to you or in what order, please come talk to me. I'm happy to help advise in that situation. And luckily on this campus, outside of our program, there's other departments. So there's a stats department, there's a biostats department, there's business analytics, there's all other kinds of places that you can take coursework in quantitative methods beyond this. So we have an embarrassment of riches. So wrapping up then, here's my pitch for what we covered. But what I wanted to say most is what's in bold here. I want to thank all of you, sincerely. I've been so pleased with how well people have been able to do this, even R. My God, I can barely use R, and now everyone here is doing it. So that's been so fun to see, and to see that I feel like there's a lot of you who are afraid or timid that have confidence now, because you can do this. And that's been great, but it didn't happen by accident, and it didn't happen without tremendous effort from all of you. So I want to say thank you for being here. It's been an honor, and I hope to see you again. I truly hope, okay? Let me know if you need anything. Office hours start in a little bit, and also next week. Okay?
Thank you.
Thank you. Should we clap it out? We all give each other a round of applause.
Do they have the emoji claps?
Yes, we do have the emoji box. And I'll stop the share so you can all see each other again. All right, let me know if you need anything. Otherwise, it's been real. Have a great weekend. Have a great summer.
Thank you.
Bye, everybody.
Thank you.